This lesson is part of Module 2 of the SaferAfrica Road Safety course. The module is focused on data, data collection, data management, data analysis and the relation between data and road safety policy making. The module is based on information from different courses and put together for the EU Safer Africa project. The course will be presented by Martin Narvabi-Niaki and Henk Stipdonk. You will hear our voices mostly, so in case you wonder who you are listening to, we'll introduce ourselves briefly.
In the first two lessons, we discussed the importance of data with a focus on crash data. Today we will focus on safety performance indicators as the crucial factors of travel behavior that denote crash risk the most. This is the outline of today's lecture. In the first part, we will discuss risk factors associated with different aspects of travel, such as vehicles, infrastructure, and human behavior. In the second part, we explain the concepts of safety performance indicators, the definition, how they relate to risk factors, and how the concept works in practice. The third part is dedicated to the common examples of SPIs in high-income countries, and you should note that these may be different from the relevant safety performance indicators in your country. Finally, we will present a checklist to develop relevant safety performance indicators. I'll refer to them as SPIs that can be used in your country, and the ways to measure actual values of these SPIs. This part of Lesson 3 focuses on the SPIs. We distinguish, as before, three main regions for which SPIs are useful: roads, vehicles, and human behavior. But first, we need to revisit the road safety model presented before. This is a summary of the relations between road deaths, SPIs, risk, and distance traveled. The formula indicates that risk can be defined as deaths per distance traveled, whether it's deaths per kilometers, per miles, or per billion kilometers. You can note that risk is tightly connected to distance traveled. We cannot calculate the two separately. Of course, if we know the number of deaths and the total distance traveled, we can calculate risk, but this risk is an average over the virtually infinite pieces of trips, all with very different risks dependent on the properties of the risk. So in practice, we need to subdivide the crashes into groups with their own trips, properties such as motorcycle trips, car trips, etc. For specific subgroups and crash types, we may be able to define specific risk factors that can be associated with the SPIs. In many high-income countries, SPIs such as these are relevant. Some of these may be relevant for your country, but this does not have to be the case. Again, we denote groups of SPIs related to human behavior, roads, and vehicles. In the red rectangles, we have highlighted some SPIs that might be useful in your country. Of those, speeding and alcohol are relevant in almost every country, whereas the other two are specifically relevant for developing countries. Both can be easily monitored. In Sweden, several SPIs have been identified and accepted as sufficiently important to be given a target in the future. This means they regularly measure the situation and compare the results with the target to see if they are still on track or if they have to intensify their efforts to improve the implementation of the SPI. This table shows values in 2007 and 2015, as well as the target for 2020. This is a very sophisticated approach, but it can be carried out in your country if you have chosen one or more sufficiently important and observable SPI, and if you have found ways to improve the SPIs. Road safety policy always involves measures to improve safety. Once it is decided that something unsafe in traffic has to change into something more safe, we should find ways to monitor this change during the coming months or years. As an example, when we decide motorcycle helmets should become compulsory, we must do the following. We must see to it that these helmets meet the required quality standards and that they are easily available. Also, that there is effective enforcement in place, because without enforcement there will be no change. And finally, that there is proper communication, education, campaigns, etc. That is introduced aiming at all relevant groups. All of these activities should be monitored quantitatively. And finally, we should observe the helmet use itself and see the number of fatalities of motorcyclists using or not using a helmet. We will now discuss the essential properties of an SPI that make sense. The essentials of an SPI are explained in this conceptual model. For your SPIs to measure and monitor, you need to have both a safety problem, such as the crash types that are related to your SPI, and a safety measure that helps you improve the safety and reduce the number of these crashes. We seek such groups of crashes and measures that are mutually connected through an SPI. If the measure is being taken, monitoring of the SPI in everyday travel helps you observe the progress you are making. For example, you may choose to define the proportion of roads with a proper sidewalk as your SPI. This helps prevent pedestrian fatalities, and the only thing you need is a measure to start building these sidewalks. Someone in your country with enough power should make sure that sidewalks are going to be built and kept free of parked cars, shop merchandises, holes, etc. Here are the properties of an SPI. It should be a number ranging from 0 to 1, where 0 is a poor performance and 1 means perfect and the problem is solved. The property should tell us something about traffic and not crashes, such as the proportion of powered two-wheelers with a helmet, or the proportion of cars in motorized traffic. The risk reduction of replacing powered two-wheelers with a car is a factor of 40, while a helmet reduces the risk only by a small factor, between 0.2 and 0.5, depending on the type of helmet and speed, etc. Module 5 will focus more on the risk factors associated with specific SPIs. It is no use to define SPIs for factors that will not be subject to policy efforts. If enforcement is poor because police are corrupt, don't expect too much from behavioral changes. If road quality is not in your jurisdiction, accept that roads are unsafe as long as they cannot be designed and built according to safety formats. If alcohol is a problem, don't focus on it in your country, and if cars are rare, forget about seatbelts for the moment. If pedestrians are killed by the thousand, focus on sidewalks and safe crossings. Build them if you can. If all practical issues are a no-go at the moment, perhaps you should focus on the management structure of the country or of the city. Focus on leadership. Don't fool yourselves and each other by writing road safety policy plans with SPIs that are not going to be improved or implemented.
We will now discuss the data involved. Of course, the data you need to measure an SPI depends on the type of SPI, but there are some general rules. The ideal way to collect SPI data is to look at the proportion of distance traveled. As it is very difficult to collect data on distance traveled, we often switch to information that can be observed from drivers or vehicles or roads. Of course, it's no use looking at very safe roads if they are not representative for all the roads, or look at safe drivers when they're not representative. So we do want roads or vehicles or drivers that we use to express our SPI are representative for the lot. To be more clear about this, let's take a look at some examples. Here's the first one, drink driving. It's good to know that drink driving can be observed with alcohol testers, which measure breath alcohol concentration expressed in micrograms of alcohol per liter of exhaled air. The driver has to exhale his breath into a tester which examines the air content and tells us the alcohol concentration. The blood alcohol concentration is expressed in grams alcohol per liter of blood, although some countries express blood alcohol concentration in grams per deciliter blood, which is also okay as long as you use the unit together with the value. Please always include the units together with the value to avoid confusion. Breath alcohol concentration and blood alcohol concentration are related through a constant that may vary somewhat, but is generally close to the value in this slide over here. A blood alcohol concentration of 0.8 gram per liter is considered dangerous almost anywhere in the world. In some countries, 0.2 gram per liter is already a violation of the law. The effect of alcohol in the blood on the risk of the drivers is very steep, so the risk goes up very quickly with a higher alcohol concentration. And this means that a high alcohol concentration in the blood could increase the general risk of the driver with a factor of more than 100. To monitor drink driving, one should not only look at violations but also at those drivers who are within the limit. When your police organization starts using these testers to measure the SPI, it's important that they do not just report the violations but also those drivers within the limit. This is because when you increase testing and fining drink drivers as a measure, this will increase the number of violations, while in the end the proportion of violations might decrease, especially if you continue to increase the testing. The graphs on this slide show the results of some testing in blood alcohol concentration in a part of the Netherlands. In the left panel, you can see the number of drivers as a function of breath alcohol concentration. The number is presented on a logarithmic scale. And here we have the number of drivers with no alcohol in the blood, approximately 100,000, 80,000 approximately. And here we have the number of drivers with some or more alcohol in the blood. So here we see a decreasing number of drivers with an increasing amount of alcohol in the blood. The left panel shows the cumulative the left panel shows the normal distribution. In the right panel we have the cumulative distribution. So here we see that 95% has no alcohol in the blood, 79% has less than, well, a little, 98% has almost 2 promille of alcohol in the blood, and so on. And of course, when you increase the amount of alcohol in the blood, in the end, everyone has less than this amount of alcohol in the blood. So these two graphs can present the results of the breath alcohol testing in your country. And in both graphs, the yellow bar denotes the amount of people or the proportion of people with no alcohol in the blood. And as you can see, almost 99% of the drivers are within the legal limit in our country. The testers that are sold nowadays allow for automatic gathering of these data by microcomputers that are integrated in the testers. The next example of a useful SPI regards speed. Speed is expressed as a distance traveled within a certain amount of time. It can be represented in kilometers per hour or miles per hour, or even in meters per second, which is common among physicists. And these values can be mutually exchanged. For example, you can translate kilometer per hour into meters per second. It is important to bear in mind that all speeds are usually averaged. Mean speeds are averaged over vehicles. And if you travel from, for example, Accra to Abidjan in a truck, in one day, your mean speed might be quite different from the maximum speed that you have achieved somewhere underway, as there will have been moments that your speed was very low and also moments when your speed was high. So in practice, speeds are always averaged. Now, to express a speed in kilometers per hour or translate it into meters per second, you can apply the method on the slide. 1 kilometer per hour equals 1000 meters in 3600 seconds, which means that 1 kilometer per hour equals 1 divided by 3.6 meters per second, which equals 0.28 meters per second, which means that, for example, 21.6 kilometer per hour equals 6 meters per second. By the way, this is the speed of a subject hitting the ground when dropped from a height of 1.8 meters. This example is used in the slide because it's the speed with which a head of a person hits the ground when he or she falls from a bicycle or a powered two-wheeler without a helmet. And it's exactly why helmets are very effective, because at these low speeds, 6 meters per second, a helmet can prevent a lot of head injury. Let's do some more simple calculus. What about the time one would need to cross a 13-lane road with a middle region, such as the one over here in Accra? It's a wide road and people have ample time to cross the street. Let's do some calculations, just to get a grip of what speed actually are. So, with a width of 13 lanes of 3.5 meters wide and perhaps a 1.5 meter region in the middle, this would mean that the total distance would be 47 meters. So suppose that there's an 18 seconds available to cross this street. With 1 second of reaction time, it means that people would have 17 seconds to cross the street once the light is green. 47 meters in 17 seconds yields 2.6 meters per second, which is about 10 kilometers per hour. This is quite a speed. It would mean something like jogging speed, for example. So everyone who wants to cross the street within those 17 seconds in time would have to jog across the street. And if you have an average of 17,000 people crossing the street every day, suppose there are 40 periods of green time every hour, and suppose that there are 15 hours available for all those people to cross the street. That means there are 600 crossings a day, which means there are 283 people that have to cross the street each time there's a green light on average. These types of calculations give you help you visualize the impossibility of solutions where there's too little time to cross the street or too little room for people to be ready to cross the street. In this graph we see how speed becomes more and more lethal in the case of a car crash hitting a pedestrian with this speed. The blue line over here represents the probability of a pedestrian being killed at the speed given. So here we have an 80 km per hour speed, and the probability for a pedestrian to be killed at that speed is 70%. The two other lines represent the error bar, the uncertainty in the calculation. So it is clear that probabilities to be killed are high. By the way, this is for cars in high-income countries where most cars do not have bull bars, so this is supposing a crash-friendly front. As to the risk factors associated with speed, the relationship between average speed and risk is often researched, but it is still not very well understood. Different researchers come up with different opinions, mainly because quantitative results are not always interpreted easily. So here we have an interesting graph taken from a 2007 report by Rune Elvik. It's a very interesting report, and it shows how risk increases with average speed. Over here you see the relative risk, which is 1 at 0 speed, and then increases with increased speed, and this increase goes faster and faster with increasing speed. And according to this graph, the risk increase follows actually a simple formula. 1 kilometer per hour increase causes a 3% risk increase. And there's another report by Finch that confirms this result. So although this seems to be very simple, we have in the road safety literature several other publications that are often referred to. And this is Nilsson, which says that risk increases with a fourth power of speed. And Elvik himself suggests that risk increases with a certain power of speed, and this power is low for low speed. For example, at the speed of 50 kilometers per hour, it's about 2.2, whereas the power goes up and reaches 3 at 70 or 80 kilometers per hour, and finally a power of 4 or even more than 4 for high speed. All these reports are generally not wrong. It's okay to use any of them, but my suggestion would be to use the results of Finch in a general sense. 1 kilometer per hour increase of speed is equal to a 3% increase in risk. An SPI for speed should be expressed as the proportion of distance traveled within the limit. And if you want to be more practical about this, you should use the proportion of observations within the speed limit. If you're starting observations with a speed detector, you could just count the number of vehicles passing within the speed limit, and the proportion of vehicles within the speed limit would be your SPI. And of course, when speeds are low due to congestion, this doesn't count because the speeds are then forced by congestion. But then on the other hand, if there's congestion all the time, speeds are low all the time. So actually you have a situation where all vehicles are within the speed limit. For a national measure of speed, we have to distinguish between different road types. This is a common thing to do. Hence you should use different SPIs for motorways, for urban roads, for rural roads, in the least. Please note that in many countries, trucks and sometimes also mopeds have their own maximum speed. And this means that when you're doing monitoring, you should take care to make a distinction between vehicles that could drive up to the posted limit and vehicles that cannot drive a speed up to the posted limit because they have a vehicle limit that is less than the posted limit. Here we see some results of speed observations on two 30 km per hour roads and two 50 km per hour roads. On the left we see the number of observations as a distribution. So here we see the speed in kilometers per hour, and vertically we see the number of vehicles with that speed. And on the right panel we see the speed, and then on the vertical scale we see the number of vehicles with a speed at most of that value. So of course all vehicles have a speed that is less than or equal to 80 km per hour, and hardly any vehicles have a speed less than or equal to 5 km per hour. And here the cumulative distribution goes up by contrast of the normal distribution that shows the number of vehicles at exactly that speed. Now what do we see? To start with, we see a funny sharp cusp at this value here, 29 kilometers per hour, and for this other road we see this cusp at 33 kilometers per hour. And it's interesting to think about why this could be this could happen. What explains this effect? My explanation is that there are some vehicles that stick to the limit very accurately and just stay below it. And then the next question would be, of course, why there's a road with a cusp at 33 kilometers per hour. My suggestion is that this road at this road the observations were done with a speed measuring device that was not calibrated correctly, so that actually those speeds are slightly less than the speeds that are shown here. You will always, when you're using data, using observations, data of observations, you always have to be aware that your data can be corrupted in some way. Now, another thing you can see from these graphs is that the roads with a speed of 30 km/h have a wider distribution than the roads with a speed limit of 50 km/h. So vehicles have a speed distribution that is shows that speeds are closer to the speed limit for higher speed limits than for lower speed limits. As you can further see is that for the 50 km/h roads, more than half of the vehicles have a speed above the speed limit. We have the speed limit of 50 km/h over here, and here we see that about 50% of the vehicles drives a speed of approximately 50 or above. So all those vehicles have a speed limit, have a driving speed that is higher than the speed limit, which suggests that the speed limit here is not very credible. It is very easy and very logical for well, at least half of the vehicles to have a higher speed than the speed limit. You always have to ask yourself why people are speeding. Are they speeding because the road isn't well designed, or are they speeding because their behavior is to be criticized? It is often the first and not the second. You can't ask from people to stick to the speed limit if the speed limit is not well supported by road design. My last example of a suitable SPI is a safe vehicle fleet composition. In many high-income countries, a safe vehicle fleet is considered a passenger car fleet with a high average Euro NCAP score of cars. But in many low and middle income countries, most of the fleet consists of power two-wheelers. And although these are very practical and very efficient, they are not in the least safe. It would therefore be a very effective policy to migrate your vehicle fleet towards a transport system where power two-wheelers are replaced by cars, or by a public transport, or by walking and cycling in the case this can be done on safe roads where there are no motor vehicles. To estimate the risk of different travel modes, one needs crash data and data of distance traveled. Such data is not readily available for many countries. So in this course we present the results of a risk analysis in the Netherlands, while assuming that the risk differences between power two-wheelers and car, or between power two-wheelers and public transport, are more or less equal to the risk differences in other countries. And of course the risk in the Netherlands would be different from the risk in your country, but the idea is that the risk differences for different travel modes would apply to your country as well. In the Netherlands we have seen also in the second section of module 2 that power two-wheeler risk equals 60 deaths per billion kilometers traveled in the Netherlands, while that of car occupants equals 1.5 deaths per kilometer traveled. So we have this value for power two-wheelers and this value for passenger cars. In between are walking and cycling with 12 deaths per billion kilometers. And then we have public transport in buses, so not trains but buses, so it would be road public transport. In the Netherlands we have 0.1 deaths per billion kilometers traveled as a passenger of a public transport bus. So when you look at the difference between the risk for power two-wheelers 60 and public transport 0.1, this yields a difference of a factor of 600, which suggests that if you succeed in transferring your traffic system from a power two-wheeler driven system to a public transport system, you would gain a factor of 600 in road safety. So from this insight, the introduction of an effective and efficient public transport system is highly recommended. Introduction of passenger cars, even second-hand and less safe cars, in order to replace power two-wheelers would also be a very interesting transition for many low and middle income countries. The ideal SPI would be what proportion of travel is undertaken in a safe vehicle, it is a car or a public transport vehicle. Here we see the Dutch data on distance traveled by car and by motorcycle and by truck and van, just as an illustration of how these data of this SPI could look like. So these data in the Netherlands are available since 1950, and here we see a graph showing the data between 1950 and 2000. In 1950, the total distance traveled by car would equal something like 3 billion kilometers annually, and this number increased to 10 billion kilometers in 1960 and to 50 billion kilometers in 1970, and from then on the increase became a little slower until in 2000 it reached about 100 billion kilometers traveled annually. As compared to that, power two-wheeler distance traveled was much less. It was about 1 billion kilometers traveled, so it was 1/3 of the total distance traveled by car, and it has been going up and down a little, but it is still around 1 billion kilometers traveled. So whereas it was 30% of total distance traveled in 1950 in the Netherlands, it is now about 1% of total distance traveled. So the composition as SPI in the Netherlands has increased enormously over time. If you do not lay your hands on data on distance traveled, you could even use data on fleet size. Here is an example of the fleet size of mopeds in the Netherlands, also between 1950 and 2010 this time, and we can see that fleet size increased to about almost 2 million in 1970, with more than 600 people killed every year as a moped rider. And then shortly after 1970, the Netherlands introduced the compulsory moped helmet, and from then on moped use decreased strongly. It also became more safe because the moped helmet improved safety, but a much more important effect is the decrease in the use of the moped. As we can see, the moped fleet decreased strongly.
In this final part of this section, we invite you to think of ways to develop your own SPIs. You are supposed to stop the presentation after each slide and answer the questions for your country. A first important property of the SPI of your choice is that it constitutes an important risk factor. If you choose your SPI, think of how many people could be saved. Don't think lightly about this property. If 10% of your population uses a car and 70% uses a powered two-wheeler, then 100% seatbelt use is going to save far less than 1% of the road deaths in your country. So take the time, if possible, discuss this subject with others. I suggest you think of 4 to 5 possible SPIs that represent a high risk factor in your country. At this step, you are encouraged to identify a way to observe your country's SPIs. If you choose seatbelt, and if you want to improve seatbelt use, you need to be prepared to observe seatbelt use in traffic, and not just seatbelt use in crashes. Perhaps for each of the SPIs you described in the last slide, you could think of ways to observe this SPI in everyday traffic. Take a short pause and if possible, discuss this among yourselves. The next step is that you visualize actual measures. If you want to improve seatbelt use, you should develop a practical implementation of a policy. For example, police roadside checks with the administrated fines and a targeted number of administrated fines for police forces. Please think of practical means to change travel behavior in your country such that the desired SBIs will improve. If you cannot think of such a measure that is actually going to work, it's no use to define the SBI and start observing it because nothing will change without a measure. You have now looked at possible SBIs with a high risk and high impact on the number of road deaths that may be saved. You have thought of observing this SBI and of a measure that is actually changing travel for the better. Now you need to take the most important step and think of an actual next step to make this change. Talk to a minister, present a plan and share it with the press, implement a change in your police force, and start a policy development plan in your municipality. Anything that would make a small step towards implementation of your change is a great improvement. And I hope to hear from you sometime about how you made your plans work.